To welcome the Tim McKenna Associate Professor from Carnegie Mellon, some guy named Noah Smith. As many of you know, Noah did his PhD here, finishing in 2006 after he was an undergrad at University of Maryland. He is well known in the field. He's taking over SIGDAT now as the new Secretary.
Secretary Treasurer.
He's yeah, as the new, as I said, as the new Secretary Treasurer, succeeding Deputy Urowski. He's long tenure in that role. Noah has a recent book called Linguistic Structural Prediction. So if you want to know how to do structured prediction in NLP, that is an excellent starting point. And he is very pleased to be giving an algorithms talk today because people keep asking him to talk about his applied work lately at the intersection of NLP and social sciences. So looking at text to see what's going on in, say, political science or in finance. I guess I should say something while Noah's moved on and is doing all kinds of stuff that nobody here would ever have worked on. I should say a few words about his time here. Oh, not because it was bad, just because we had fun. So I went back and I looked at the recommendation letter that I wrote for Noah when he was on the job market, in which I told many anecdotes and said many superlative things. But I mentioned the week that he came back from his honeymoon, and I happened to be away that week. So during that week...
Honeymoon. It was 3 days. So my wife is still angry that we didn't get a real honeymoon. But I'm not blaming you. It's not.
Maybe you should take her to April. So I happened to be away that week, so the cat could have stayed away for, well, the cat was away, the mouse could have stayed away for another 7 days. But I came back to find that he had come up with 2 ideas for new projects, implemented them, run one of them on 13 languages, and gotten performance gains, started writing the paper. This was in the first week of his married home life. And in that week, he'd also extended some software for the use of other students and started learning about some new NP-complete optimization techniques and revised the journal paper and some other good stuff. And through his whole time here, Noah's astonishingly productive. And because he has continued that pattern in his 6 years now at CMU, I'm not able to summarize all of his work. So I'm just going to let him talk about that. Thanks, Noah.
Thanks, Jason. It's always a pleasure to come back to Hopkins. I think this is the first time I've come back in any kind of visible capacity to give a technical talk since I left almost 6 years ago. So I'm excited to be back, and it's really strange to see both the new building and also the fact that there's been so much turnover in the faces. So I've been enjoying meeting new people and catching up with old ones who didn't used to be here, but kind of surreal experience that one day I'm sure many of you will share. Anyway, so today what I'm going to talk about is a particular new algorithm called AD3. This is primarily the work of Andre Martinch, my PhD student, who's going to be defending on May 11th. He's enrolled in a dual program between Carnegie Mellon University and IST in Portugal. So he has a couple of advisors over in Portugal, Pedro Aguiar and Mario Figueiredo, who've been a pleasure to work with through Andre, and also he's co-advised at CMU by Eric Xing, who's a co-author on much of this work. Later in the talk, one of the example applications I'll talk about to frame semantic parsing is primarily the work of Dipanjan Das collaborating with Andre. Dipanjan is also finishing soon, so shortly my lab is going to have tremendous turnover, and I'm going to miss all these people very much. But today I will talk about their work. So here's a natural language sentence. It's a nice example. We'll use it throughout the talk. And I'm just going to put forward one of the things you might want to do to it is analyze it into some deeper meaning representation. So one meaning representation that we've been working with recently that it has some nice things to offer is frame semantic parsing based on the FrameNet lexicon. I don't know, actually it looks like some of the colors may be coming up strangely. The idea is that your content words like professor and chuckled and unabashed and glee evoke these deeper abstract conceptual frames like make noise, each of which then have you can think of them as predicates, and they've got arguments that can be found to be filled by roles found elsewhere in the sentence or maybe outside the sentence. So in this case, the word chuckled evokes the frame making noise, and we know because we use the word chuckled that this also tells us what kind of sound was being made. A chuckle is a particular type of sound, and we know who made the sound because the professor is filling that role for this particular frame called sound source, and then this frame has something else called internal cause. So this is a lot like prop bank, except that you've got abstract frames and you've got roles that are specific to the frames, not these abstract arg0, arg1, arg2 type roles. But the basic idea is that this is a way to represent very basic predicate argument structure. It's an intermediate step between deeper semantic analysis and simple sense disambiguation or semantic role labeling. So in any case, here's a problem. How do you, once you've known, let's say you've already figured out which words evoke which frames, how do you know which arguments are filled by which parts of the sentence? So one way to set this up is to say we just want to solve this argument identification problem. We've got a sentence, we've got a labeled predicate, and we want to find all the arguments that are filled in the context of that predicate. So we have a couple of constraints. We know that each argument is filled by at most one span, maybe. Let's keep it simple. And that the spans probably shouldn't overlap, right? So we're looking to find pieces of the sentence that don't overlap and fill as many of the arguments as are filled, but no more, and each one only once. So I'm going to start introducing notation gently. Let's let y hat sub a be the sort of best span for a particular argument A. But then what we really want to do is we want to solve this global problem and find all of the arguments for the particular role. So we'll use bold y hat and maximize over the whole set of y sub a's. And we want to maximize the sum of those scores. And then I'm going to be a little bit hand-wavy. I'm going to use blue ink for being hand-wavy and say that some constraints hold, right? And these are going to be my overlap constraints and my constraint that each argument is filled by at most one span. So this is just sort of a computational, semi-computational way of setting up the problem. And so, I don't know, one kind of interesting thing that happens when you start reading about FrameNet and looking into the lexicon is you discover that there's a lot more in there than just the set of abstract concepts and the kinds of things that fill the roles. There's a tremendous amount of linguistic knowledge. For example, certain kinds of arguments require each other. You can't say blueberries resemble. They have to resemble something else. There has to be a second argument there. You also can't. You have exclusion constraints. You can't say his temperature fluctuated between 101 and 105 degrees to only a mild fever. You have to say ending in only a mild fever, or have some other predicate there, right? So these kinds of things are actually encoded in you can take a look. You can browse FrameNet online. A lot of these kinds of constraints on which arguments are present or absent are expressed in FrameNet. And so, the kind of high-level research program in my group is that we don't really want our linguist friends who are thinking up good ways to represent deeper structure of language to be constrained by the computational formalisms that are available. We want them to be able to dream up something more exciting tomorrow and then incorporate it into our frame semantic parser. And another direction is we'd really like these kinds of analyses to be more integrated with other types of analysis, like syntactic parsing, or tagging, or morphological analysis. We'd really like to be doing joint inference over all of these things and using cues from one level to disambiguate the other. So this talk is about AD cubed, which is a decoding technique, just solving this inference problem, finding the best structure, when you've got many overlapping constraints, which could be hard or soft. And usually in this setting, we're going to find it's particularly convenient to talk about them in terms of first-order logic expressions. Okay, so this might I'll give examples from the general field of linguistic structure prediction, but if you're a Markov logic network person, or you are particularly taken by grounded Markov logic nets, this is really well suited, we think, to application in that general setting. This algorithm is often exact, and when it is, it has a certificate. When it's not exact, you can embed it within a branch and bound search, and I'll do that very briefly at one point in the talk. I don't think that's a particularly deep result, but it might be useful. I guess I should say what AD cubed stands for. It's alternating directions dual decomposition. So this algorithm is closely related to dual decomposition techniques that have been discussed primarily, I guess, initially in NLP in work by Rush and colleagues, but it's also, I guess, Adam Lopez has a nice paper with Michael Owley using dual decomposition for CCG parsing. This is sort of a different take on dual decomposition. And I'll try and show you that connection when it's convenient to do so. Okay, so let's talk about decoding in a somewhat generic way. This is just the same expression I had before, except now I'm just going to divide my structure y into we'll call them local parts. Okay. Now if you think about, let's let this set of parts be denoted big R, and we'll use y sub little r to be the local part setting for the rth part, and you can think of these as like variables in a graphical model. And then the scoring is going to depend on components. So I'm going to use the words parts and components to have two different meanings. I know that can be confusing. These are the best words I've come up with. So components are going to be pieces of that score that they'll be indexed by S, and each component is only going to depend on a subset of all the parts. So we'll call that R sub S. The components can overlap. They can share some parts. Okay, that's fine. You can think of these scoring components as soft factors in a graphical model. And we're also going to have constraints, and we're going to assume that the constraints are also local to components. So you can think of a constraint as a hard factor in a graphical model. So here's a familiar example to make this a little more concrete. If y is a sequence of labels, and I let my parts be positions times labels, and then I let, or maybe pairs of positions times pairs of labels, then I can let each score depend on adjacent labels. So this could be a component, looking at the ith word and giving it label L, and the I plus first word and giving it label L prime. And then the constraints somehow have to enforce that we have a valid sequence, right? That everything matches up nicely. And so this is a nice familiar example. You can solve it exactly with the Viterbi algorithm in polynomial time, and this is often used for things like part of speech tagging. Another familiar example is context-free parsing. So Y might be the derivation tree from a context-free grammar. R might be spans of the sentence times labels, on terminal categories. Each score might depend on a parent node and its children in the tree. The constraints could enforce grammaticality under our context-free grammar, and you can solve this exactly with things like CKY in the early algorithm. Okay, so you can get phrase structure parsing. I give this talk to people who aren't NLP people, so I have to show them what a phrase structure parse looks like. Yeah.
Sorry, no unary rules in this formulation.
You could have unary rules.
Well, you wouldn't know.
You'd probably have to extend your definition of what your parts are if you did that.
You'd need to change that.
You might need. You might, although under the usual assumptions, you would never have an infinite chain in the best tree, right?
Right, so you can simplify the problem.
Yeah. Another familiar example is dependency parsing. This is certainly a favorite for people in my group, and I guess Jason's as well. Y might be a directed spanning tree, representing the dependency structure of the sentence. R would be positions times parent positions. The scores might depend just on child-parent pairs, or bigger chunks of the tree, larger components, which we'll see later in today's talk. The constraints might include that the whole thing together has to form a directed spanning tree, or maybe a context-free derivation under a context-free dependency grammar. Depending on which of those two, you might use the Eisner algorithm or the Chu-Liu-Edmonds algorithm to find the best structure. So here's the picture of a dependency tree. Okay, but in general, it's kind of useful to write down the problem at this sort of level of abstraction and say that we're going to have parts, we're going to have components, and we're going to have constraints, and there's usually more than one way to define the parts, components, and constraints to solve a given problem. I think this is actually a really important thing to remember. So to take an example for dependency parsing, back in 2006 there was a nice paper showing that you could solve the dependency parsing problem using an ILP, but it had an exponential number of constraints. And so later, Andre and I and some other colleagues had a paper that showed how you could reduce the number of constraints to something polynomial. And the representation was just drastically different in the way that you defined the problem into parts, components, and constraints. This general idea, sorry, I have to do some shameless self-promotion, of abstracting away from different kinds of linguistic structure and using the same kinds of methods both to learn how to do the prediction and to do decoding. At the end of the day, this talk's just about the decoding, is put forward in my book, which I hope you will enjoy. Does Hopkins, can you get it for free through Hopkins? Excellent. So you don't even have to pay money. Just download it, print it out. I did not. I only have a very limited number of paper copies, but only old people like paper copies, Mark.
I was thinking of Jason.
I think I gave Jason a copy. He probably wouldn't like it anyway. Okay, so let's be a little less hand wavy about constraints hold. So what I'm going to do is I'm going to replace this idea that with something more concrete and say, for each of the components, we're going to have a notion of feasibility. We want the constraints we want the solution for a particular component y sub s to be in some predefined set big Y sub s. So this is just saying that I have a good, I have a valid local solution for each component. And then beyond that, I want to make sure everything agrees. And so one nice way to do that is to say, well, there's a Y bar. I don't know if you can actually see the bar on top of this Y. There's a bar on top of the Y. And so I'm going to have Y bar, which is a copy of the global structure that I'm going to call the witness. Okay, so this is just a solution to the global problem. Notice that it's not scored directly up here, but I'm going to constrain it so that for each of the local components, y sub s, the parts of subproblem s that are in R sub s have to match the witness vector. I don't know why this isn't rendering well. This has a bar over it. So this is the rth component of the witness vector, and this is the rth component of y sub s, the solution to the sth subproblem. Okay, so the witness, I think I have a picture that'll help make this clear. So here's the first order sequence labeling problem. Wow, it's not my computer. I think it's your projector. It's you. Okay. Oh. We can get... Is this the equivalent of like moving the record? Oh, that was bad. Are we back? Okay, sorry. I'll do the best I can. Wow. Okay, so the witness vector is up here, and this is just a sequence labeling of the whole thing. Okay, and so each of these little blocks is one part of the sequence labeling. It's one component. Sorry, not part, component. So one component is going to be y1, which looks at the professor and tags both words. One component is going to look at Professor Chuckled and tag both words. One is going to look at Chuckled with and tag both words, and so on for each bigram. And then each of these contains two parts, which have to match the respective two parts in the witness vector. Okay, so I'm getting global agreement. Okay, so the next step is... It's all well and good to talk about part-of-speech tags, but it's much more useful if we can convert everything into a binary representation. So the next step is to say, instead of using little y sub s, I'm going to use vector y sub s, and I'm going to represent each of these solutions to the subproblems using an indicator vector instead. So all this says is, I'm going to have a vector of ones and zeros and pick out ones for the parts that actually get used to solve each subproblem. And then the next step is to express the feasibility constraints using a linear representation. So for each subproblem, we're going to have a matrix A sub s and a vector B sub s. And this is sort of the magic part that I'm not going to go into, where you represent your structured problem using an integer linear program. And I'll just say, if you're familiar with this thing, it's kind of obvious. If you haven't seen this sort of thing before, it's actually quite simple to represent many first-order logic style constraints using linear functions on your bit vector y. And so this leads very naturally to an ILP representation. It's not always the case that there's a compact representation. So when you can find one, that's usually a nice result. For many problems in NLP, there is a compact polynomial-sized solution. Okay. So great, an ILP. We know it's an ILP because we have a linear scoring function in the different components. We have linear constraints on our variables and some equality constraints down here, which you can't read. And then we have integer constraints on the y sub s. They have to be in 0, 1 to the r. You can't. I'm sorry, not much I can do. So you've got an integer linear program. Is that a good thing or is that a bad thing? It's attractive, right? We know how to solve ILPs. People in the operations research community have spent a lot of time developing nice tools for us to use. Unfortunately, they're all proprietary. We don't really know how they work. Well, we sort of know how they work, but they're proprietary. We're not supposed to know how they work. What's the first thing you do once you have an ILP? Apart from, imagine you can't use proprietary tools. What are you going to do? You're going to relax it. So that's what we're going to do. Okay, so you get rid of those y sub r in 0 or 1 and say it's between 0 and 1. So this is a nice visualization of LP relaxation. This is my original problem. I'm looking for a point inside a polytope, which is integer, and I'm trying to maximize some function, which was represented in a gradient by this slide that went that way, so the solution is there where the star is. In the relaxed version of the problem, we get rid of the integer constraints, and we simply look for a vertex of the polytope that maximizes the score, which is where the star is here. So this is a very standard thing. There's a tremendous amount of work on using LP relaxations now for inference and machine learning. And it's just, there's just a lot of different things we could talk about. I'm not going to go into these in detail. One sort of specific area that we will go into more is dual decomposition, which is going to build on this idea of LP relaxations. One thing I would point out is that if you go and you read the Rush et al. 2010 paper about dual decomposition in NLP, I believe they did discuss the LP relaxation, this point about LP relaxations, but their method didn't actually hinge that much on using an LP relaxation. They end up not solving any LPs directly. They end up using standard combinatorial machinery to solve the subproblems. So if you're familiar with dual decomposition, it may seem strange to you that I've gone through this LP relaxation route to get here. I mainly do that because in our setting, it actually becomes more important than in theirs. But you can, I believe they told the LP relaxation story later in the paper. Okay, so the next thing to say is that using dual decomposition in NLP is now widespread. But the key thing that you'll find, so you can see it in parsing papers, CCG work by Adam, alignment, translation. The key thing you will find, though, is that the algorithm being used to solve the dual decomposition problem is subgradient descent. Okay, and so what I'm going to present, AD cubed, is an alternative to subgradient that is more attractive when you break the problem down into many, many components, large number of subproblems. Okay, so here's the AD cubed strategy, and I'll try and be clear as we go exactly where it deviates from the subgradient approach. So the first 3 steps are all the same. First, you break your score down into components and use a binary vector representation. This is usually very natural for structured NLP problems. The second step is to apply an LP relaxation to each of your components. Okay, so now you've got these nice little LPs, and things would be easy except for the fact that you've got constraints to make everybody agree with the witness vector. So the third step is going to be to introduce Lagrange multipliers for those agreement constraints with the witness vector. Okay, and all of that, those 3 steps together are more or less what we call dual decomposition. The final thing that's different, that we're doing differently from previous work, is we're tackling that Lagrangian with something called the alternating directions method of multipliers, ADMM. ADMM is an old thing. It's older than me. It goes back to the mid-'70s. But only recently we've now seen it getting attention, particularly for learning. Here we're just using it for inference. So this is how we get our name AD cubed. Alternating directions is this new old new optimization technique for solving the problem of dual decomposition. All right, sorry, more math that you may not be able to read. This was our original ILP. as we'd set it up before, and then we added, we've now relaxed the integer constraints so that each of our y bits has to be between 0 and 1, not necessarily at 0 or 1. And then the next step, oh, right, let me just make a small point. One thing that's sort of useful to remember is that if we didn't have any constraints to couple everybody back with the witness vector, we could solve each of our subproblems very easily. Right? This is kind of the hallmark of when dual decomposition makes sense. Each of the subproblems would be straightforward to solve. For Rush and Collins, they were calling dynamic programming algorithms and relatively simple combinatorial things that are really familiar to NLPers for solving these little subproblems. For us, we're actually going to land somewhere different, and you'll see why in a minute. So here is the augmented Lagrangian. So let's ignore everything at the right end that's in red for just a second. What I want you to see, if you can read it, is that I've taken the LP relaxation problem up at the right, and I've just dualized it. I've simply introduced dual variables for each of these agreement constraints down here. I'm going to suppress these feasibility constraints for each of the subproblems for now, but they actually fold in under this little inner max. So this is exactly the same problem, except I've now done the standard Lagrangian dual and introduced lambdas for each of these agreement constraints. Okay, so if I stop there and didn't have anything else, this would just be the standard dual problem. And if I tackled it with subgradient descent, I'd have subgradient DD, going back to Kamodakis and Rush and Collins. But we've done something a little different here. Can you even read this? Yeah, so what I've done is I've taken each of my subproblems and each of its parts, and the difference between that part and this is the y bar, this is the witness vector, and squared that difference. So I've added a quadratic penalty times rho that pushes more aggressively for agreement between each component and the witness vector. That's the whole thing right there. That's the only thing that differentiates us from the earlier work. It's an old idea. It goes back to the 70s using an augmented Lagrangian. At the solution, it will be identical to the original problem because that final term will go to 0. But while you're running your optimization algorithm, you've got a much stronger push toward agreement. Okay, this extra quadratic term is just a stronger encouragement. Okay, so 30 minutes in, here's the algorithm. We initialize our price vector, our Lagrangian multipliers. We initialize our witness vector, and then we simply repeat until we either find the optimality certificate, or we get there's a way to calculate primal residuals and dual residuals. If those fall below a threshold, we know we can safely stop. And we're just iterating between solving each of the component problems for each y sub s, and then updating the witness vector and the Lagrange multipliers with closed form updates. These parts follow, they're just algebra. This is the part that's interesting. We have to solve a subproblem, and it's not linear. It has a quadratic term in it because of this coupling with the augmented Lagrangian brings in this term. If I hadn't done the augmented Lagrangian, you would see the algorithm, the subgradient DD algorithm would be essentially the same thing, except for two differences. I wouldn't have the quadratic term, and I would have the same certificate, but I wouldn't have the primal dual residuals. So that's actually a nice benefit of doing things this way. You know when you can stop your iterations safely. Okay, so everything looks good, except I'm now telling you that your subproblem requires solving a QP. You should be bothered by this, right? Usually good NLP hinges on the use of respectable linear scoring mechanisms and avoiding anything complicated like a quadratic or not anything nonlinear is sort of inherently problematic, and we try to approximate it in the end with something linear. So we don't have to do that here. We'll see why in a minute. Just sort of building up. If we'd had just the original component subproblem, this we know we can solve. We sort of by assumption we said we know how to solve our subproblems. When we added, as Rush and Collins did, this extra linear term, on the y vector, we didn't really fundamentally change the difficulty of the problem. This is just sort of slightly altering the way we score the different parts when we score the different factors in our subproblem. But the form of the problem is still the same, and you can use the same combinatorial machinery because it's linear. Now we've got something quadratic, and we need something else. We need what we're calling quad inference. Okay, so what actually saves us here is that we've broken our problem into many small subproblems. Right? So if we were trying to solve big things like calling the CLE algorithm or some kind of sequence labeling algorithm or some other dynamic programming algorithm, then linear decoding machinery wouldn't obviously help us. Although you can ask me about that later because we're working toward a solution. But because if we instead represent our problem using many small first-order logic components of the kind, if you use these two arguments, if you have this particular argument to the word, you also have to have this one. Or if this one's here, you can't have this one. Simple local expressions in terms of first-order logic actually turn out to be quite easy to solve the quad inference problem for. What's really cool is that you actually can solve most of them using some kind of sort operation in n log n time in the number of variables involved. So there was this interesting result where by Dookie et al. In 2008, where they were projecting, they had I forget exactly what the context was, but they had to solve this projection problem onto, I think, a quadratic function onto a probability simplex. And it turns out that the XOR problem, or the uniqueness quantifier, is exactly equivalent to what they had to do. And you can extend that result to a whole bunch of other logical expressions, including existential quantifiers, logical assignment, at most one. There's a closed form solution for pairwise binary factors. And there are simple ways to build on these, put together these building blocks and get conjunctions, implications, universal quantifiers. Soft versions of the same constraints can be, you can just bring in another variable, set an equality, and put a score on it. So the bottom line, I guess I'll just go ahead and say that if you do want to have big factors that are complex and require calling minimum spanning tree algorithms or sequence labelers or so on, you can probably do it. We think we have a way to solve the quad inference problem by iteratively solving the original linear problem. I'm not going to say more about it because we haven't worked out the details. Okay, so I gave you AD cubed. It's a decoding technique for incorporating many overlapping constraints, which could be soft or hard. And it's particularly attractive when we can express the constraints, the components, as small first-order logic expressions. This is very similar to subgradient DD. It provides an optimality certificate when you've solved the original problem. But it also gives you primal and dual residuals so you know when to stop iterations. So that's an attractive property if you want to use this in the real world. What about when the solution is fractional? So I promised I would give you branch and bound. You can use branch and bound when you have a fractional solution. So this is just a recursive algorithm that alternates between finding a bound by solving the problem. And then if you've got an integer solution, you can quit. Then you set your bound to the objective value, and you can return u, and then pop up a level. Otherwise, you're going to branch by picking the most fractional element of your vector and returning back to repeat, splitting on that particular dimension, running it once with y equals 0 and once with y equal 1. Is this familiar? I think branch and bound is the kind of thing most people have seen at some point in their life before. So I'm glossing over this very quickly because first, we didn't have to do it very often. We find that for this particular way of breaking problems down into many small overlapping components, you rarely actually get a fractional solution. So you don't actually have to resort to this too much. So all right, now's a good time to ask for questions because I'm going to switch into experiments results. Yeah. So you can think of this as semantic role labeling, but we wanted to remind you that we're using FrameNet, not PropBank. That's right. Which was based on FrameNet, not PropBank. That's right. we could keep calling it semantic role labeling. So the other reason is that when we actually write papers about this, so the Das et al. 2010 paper, we didn't just do the role labeling, we also found the predicates. And so we wanted to use the word parsing, but then semantic parsing means something else. So yeah, we're not trying to be crafty, we just wanted to be accurate. And yeah. You can think of the part that I'm talking about as semantic role labeling. Yeah. Okay, so here's the problem we're trying to solve. We've got we're just solving the argument finding problem, so just the semantic role labeling problem. So we actually have a system that we implemented in earlier work called Semaphore, which uses a beam search to find the fillers for the roles of a given predicate. So it's actually a two-stage system. First it labels words, and then it goes looking for the fillers of their roles. We haven't found any kind of joint inference to help at all for this kind of problem, so we focus mainly on finding the arguments, which seems to be harder. And we've got these constraints that there's at most one span per role, a uniqueness constraint, and there's no overlap among the spans. These are relatively straightforward. There's work by Dan Roth's group that's been doing this for a long time using ILPs. There's nothing new there. The only thing we're adding are these FrameNet-inspired pairwise exclusions and requirements that are in the lexicon. And so this is kind of a nice question. Can we do better on the task by respecting these constraints? Or can we get perhaps qualitatively better parses that respect the constraints and make more sense without sacrificing accuracy on the standard criterion? And the way I said that actually sets you up to conclude what the result will be. But here's, just to give you an idea, the components that we have, they map exactly onto the constraints that I described. And the number of components we have depends on the size of the lexicon, the number of roles for the frame, the number of words in the sentence. Each of them can be solved in n log n in the size of that component. These little diagrams here are from an earlier version of the talk when I tried to explain to you exactly how we relate these little logical constraints to solving a problem on the simplex. I don't think you can read them well enough to make any sense of it. Okay, so in our experiments, remember we're mainly focusing on runtime. What we found was that so we compared it to the beam search that's built into the original Semaphore system. We're comparing to Cplex, which is again proprietary, built in parallelization and all kinds of other good stuff. It's a great system, and also to our method, which could probably be parallelized, although we haven't done that here. So I'm going to focus on runtime, but let me point out, if you just do a greedy local prediction, don't worry about any of these constraints. You can get 67 precisions and 59 recall. Yeah.
So a while back you mentioned what your constraints are. One of them was no overlap among argument spans.
Yeah.
I want to ask about that. I mean, oftentimes you have one argument contains the other. One argument might have that incentive.
Yeah.
So that's the kind of thing that you're.
We could be giving up on that. It's worth finding out whether this helps or hurts. You could soften the constraint, and that's a trivial move inside our system. We haven't tried it, but I believe that was we made that decision. So I'll just a little bit of background on this task. FrameNet doesn't describe exactly what it means to get a frame semantic parse of a sentence, right? It's not a computationally defined problem from them. We had to sit down and decide exactly what we were going to look for and not look for. And we knew we wanted to go farther than what Gilday and Jarofsky had done, but we also had, we wanted it to be computationally feasible. We made this decision, right? In our system, we're only going to find things that don't overlap. But if you adopt this, if you stuck with beam search, that would certainly complicate matters quite a bit. With this framework, you could actually test out this idea and see how much it changes your decoding problem. It's probably worth doing, although I seem to remember when we looked in the data, we didn't see that many actual overlaps. There were a lot of AD3 rule type decisions when we decided what the constraints were going to be in pretend. That's right.
Oh, but if arguments are different predicates,
That's perfectly okay. Right now we're solving each predicate separately. Yeah. But you never know. Yeah. Okay. So So all of our models are getting essentially the same performance, which is a little bit better than the greedy local prediction, right? So I'm not gonna compare the numbers because they're all essentially the same in terms of accuracy. What we found was that the constraint violation. Well, we know that the accuracy measure that's used for this task, dating back to Semival 07, doesn't pay any attention to these kinds of constraint violations. So we didn't expect to get better performance. The question was actually, what it ended up being was whether respecting these constraints was going to hurt us, right? Were we going to lose precision and recall? It turns out we don't. What I guess the real point here is that you can respect these constraints. If you use Cplex, you're going to pay quite a bit in runtime. So you can get beam search down to under 3 seconds for the whole test set. But you're violating about 50 requires constraints. And widening the beam doesn't change that. It's not trying to respect any of those constraints. I think in the original paper we had the beam at 100. And it was taking a whole half a minute to parse the data. We can get essentially the same performance with a much smaller beam. But Cplex can avoid the constraints for you, even with the LP relaxation and not solving the ILP directly. But it's going to cost you quite a bit. We can use AD cubed and get rid of all or almost all of the constraints, depending on whether we apply branch and bound at the end, and parse the whole thing in under 5 seconds. So we thought this was a nice result. If you wanted to run semaphore on a web scale data set, this time savings would be pretty significant. You might.
Because the constraints might, force you out of a bad interpretation into a better one by shifting something from one role and forcing something else to be labeled.
Yeah.
So
That was our naive, optimistic hope, but yeah, it didn't. So my suspicion is that if you dug around in FrameNet more, you'd find more things that might help you more. Right? We basically picked a couple of constraints that seemed like pretty natural for this part of the problem, and seemed to be pervasively applicable enough to give it a try. There are a lot of funny little corners of FrameNet where it seems great, but it's not clear that it's actually going to affect real data. So we wanted to start somewhere that was likely to actually apply in the test set. One other caveat here is that the data sets, there's now a new release of training data, which is what we're working with here, but we're still talking about relatively small amounts of training data. This is not Pentree Bank sized. So I think maybe we just don't yet have enough data to be able to see. Quite possibly, or nouns, yeah. So another difference between FrameNet and PropBank is that nouns can evoke frames as well, right? Destruction. Yeah. Okay. So now let's talk about dependency parsing. So we have a parser called Turbo Parser, and we don't call it Turbo Parser because it's fast, although it's getting faster now. We call it Turbo Parser because this idea of representing the parsing problem as a graphical model and then applying methods like belief propagation, as done by Jason and David Smith, is very similar and we think intellectually close to the idea of turbo codes, which are these error-correcting codes. There's this interesting intellectual history where algorithms used for decoding error-correcting codes turned out to be really similar to algorithms used to do inference in graphical models. And so inspired by that, we call this Turbo Parser. So here's the dependency parsing problem. Just to ground you in the way we think about it, you can say that the basic parts of this problem are the links, the arcs between parents and children. So these two parts are used in the tree I showed on the last slide. This one isn't. And then maybe you have another part that says another component that says, I want this to form a tree. And so this was a really nice idea by David and Jason, where they said there's this one additional component in the problem that requires all of the, or one factor, I guess was the term they used in the factor graph terminology, that requires that all of these arcs together form a well-formed dependency tree. Another way to look at it is that you've got a whole bunch of components defining a multi-commodity flow problem. And you can do that in a cubic number of components, which we did in 2009. So this kind of, I'm going to skip over the multi-commodity flow representation. It's a neat paper, but it would just take too long to go into it. It basically has a bunch of components that enforce that you've got directed paths through the graph that makes sense in that they form a tree. But we can have other kinds of components too. So we can have things that look at grandparents by conjoining two arcs that share a node in the middle. You can have any sibling pairs where you've got two arcs that share a parent. You can have where did they go? We can have consecutive siblings, which use a head automaton model, which is what was done by Rush and colleagues. You can have non-projectivity, something that was kind of different in our model. You can have head bigrams, where you look at two arcs. You can look at the parents of two words that are next to each other. And all of these things end up having quadratic or cubic numbers of components and n log runtime. I'm sorry. They all have at worst cubic, but the ones that have n log n runtime are all quadratic. So our final runtime for one iteration should be n cubed log n.
And just to be clear, when you say runtime, you mean the runtime of
solving the quad problem for that. That's right, for that component. Right.
And so this is a lot like the chart that we had for the propagation parsing stuff.
Indeed.
Where it was the runtime was the runtime of propagating messages.
The messages. That's right.
And you have more or fewer factors, and the larger ones tended to take longer.
That's right.
But there are fewer of them.
Exactly. Okay, so the experiments I could show. I have a hidden slide here that will show you all the numbers, but I think it'll just make your head spin. I'll give you the short version. There are about 15 dependency parsing data sets in different languages. We trained our model using cost-augmented Mira with LP relaxed inference. So this is something that actually another nice thing about LP relaxations is that you can train your model using the LP relaxed version of inference, and under certain settings you can still get a nice model, despite the fact that you've used LP relaxation. And there are theoretical reasons to think this is actually perfectly justified, and you're not sacrificing much. We didn't use any kind of branch and bound here. We just used fractional solution rounding with CLE algorithm. And what we found was that in 7 out of the 15 cases we win. The Ku et al. Model wins in 5 cases, 2 wins for our earlier model, and 1 win for Ku and Collins 2010. And just to give you an idea, again, I give this talk to non-NLP people. The current state-of-the-art in dependency parsing is about 77 at the low end for Turkish, up to about 93 for English. Okay, and so we could be doing quite a bit better in some languages. What's really cool about this, though, is the convergence. So I'm going to talk about the full model first. So what you're looking at on the y-axis here is the unlabeled attachment score as we run more iterations. And so if we run subgradient with the full model, we don't actually converge within 1,000 iterations. So this red line, if you kept running it, it should eventually get to where the blue line is. But you can guess it's probably going to be a while before it gets there. It should converge to the same solution. So this is the many components version of our full model, which has about 3,000 components per sentence. The maximum number in our data is about 100,000 components. If you use AD cubed, which is the blue line, you converge, as you can see, much faster. Now, it's also worth asking, if you have a slightly simpler model, can you get this level of performance? And what's kind of compelling, I think, about AD cubed is that the dashed lines here are the second order models. And what you can see is that AD cubed gets a little bit higher than the subgradient method. So it does ultimately get to a better point. We can't actually run exactly the same second order model that was used for the subgradient. So this is the Ku et al. Work where they had about 310 components. I think there's a head automaton in there. Our version, it's representing the same problem in a different way. It has a lot more components, and it gets slightly, it's about on par with performance. Where you see the real difference between the two methods is when you move to these many component problems. Okay. When you compare with simplex on this, cplex on this problem, on average we're doing a little better, about a third of a second per sentence. Cplex is a little more than half, and where we seem to be winning is for sort of down at this end and up at the extreme end for the really expensive problems. In the middle, cplex actually seems to have a slight advantage. Somehow this works out to our benefit on average because we're really, really fast on the short sentences. Okay, almost out of time, so I'll just tell you some things I left out. In frame semantic parsing, more than 99% of the time we're getting the exact integer solution. In dependency parsing, we got optimality certificates on more than 80% of the sentences in fewer than 300 iterations. So that's a really nice result. Subgradient, by comparison, only 30% of them in 100 iterations for the full model. 1,000. I didn't talk much about these primal and dual residuals for stopping criteria. If you look in the EMNLP paper, there's a formula. It's quite simple, very easy to calculate whether you're close enough. I mentioned that there was this row hyperparameter that tells you how much extra penalty to put on the quadratic, the square difference between your witness vector and each of your component vectors. We dynamically adjust it. That's explained in the paper. It gives us, I think, some speed up. We had some experiments on synthetic Markov random fields, pairwise Markov random fields in the ICML paper. You can take a look. And there's a whole lot of boring detail I could tell you about the quad inference problem and how to solve it for each of these different kinds of factors laid out mostly in the appendix of the EMNLP paper. It just didn't make good material for a talk. So if you want to know more, that's the place to look. Andre's thesis coming out in a little more than a month should have that in even more gentler detail. And you can download these things. So Semaphore is online and available. TurboParser's been around for a while. I don't think that the current version of TurboParser incorporates AD3 yet, but it will soon, I'm told. Okay, so I'll wrap up. AD3 is a nice new decoding technique that makes sense when you've got lots of first-order logic expressions to constrain or score your solutions to your linguistic structured prediction problem. I think as we continue sort of changing what linguistic structure looks like, adding more detail, trying out new ideas for different kinds of representations and integrating different levels, we're going to want these kinds of declarative specifications, and having the algorithm match our original declarative specification has a lot of advantages. We're finding. So I'll close by sticking up the list of papers you can go read if you want to know more, and acknowledging, again, this is primarily Andre Martinez's work. He really doesn't look that pale, and Dipanjan Das on the frame semantic parsing work. Happy to take questions. It might be very expensive, right? Yes.
So, and when you said that you found the exact solution, was that applying only to the frame semantic parsing? I mean, those numbers you showed up at the end, 98.9%.
That was frame semantic parsing, yeah. The 80% was dependency parsing, yeah.
So in that case, were you also doing?
We didn't do branch and bound there. We actually hadn't thought about it that carefully. We just used rounding with Chulu-Edmonds. So we take the fractional solution to define a spanning tree problem and find the spanning tree closest. It's basically a projection. It was borne out in the empirical results that this wasn't hurting us.
In branch and bound, how do you do the variable value order?
So you're asking how do you pick which element of the vector to split on?
Yes.
We pick the one that's the closest to 0.5. We could probably do something smarter.
There's a whole literature on this. Just curious.
For 0.2% of the time, it wasn't. No. It will come out. I don't know in what venue. It was rejected at ACL. If it doesn't get accepted this year, we'll probably just make it a tech report.
well, we're just about at 1 o'clock. So why don't we thank Noah again, and I think there are some students taking them to lunch.
Great. Thank you.